In today's lesson, we are going to be furthering our study of probability, and we're going to start to look at sort of the rigorous mathematical way that we're going to be defining probability for this course. And so we'll be thinking about what are the properties that define a probability, as well as sort of how do we interpret probability? How should we be thinking about uncertainty to resolve it in this course? So, really what we're sort of focusing on today are what I would call the axioms of probability. And these are the sort of basic building blocks that tell us whether something's a valid probability function or not. And then from there, we can get all sorts of useful properties out of our probabilities that can let us answer questions that become more and more interesting as we move on. In terms of what we're hoping to cover with the lesson today, we want to understand what's called the frequentist interpretation of probability. This is going to be the dominant way of us thinking about uncertainty in this course, and so it's important to sort of grab a basis for that. We're also wanting to understand those three basic building blocks, those three axioms of probability. And the idea here is that we use those as sort of a definition for what probability is, and then we work to build up more useful properties from there. We also want to learn how we're going to understand and manipulate the probability or properties which arise from those axioms, right? So how can we get even more useful results out of those axioms? And so we'll see all of that in the lesson today. And to begin, I have a question, and I'd actually sort of encourage you, if you're watching along with this, to perhaps pause the video here and think about your answer to this question before sort of give an answer to it. But the question is, what do I really mean if I say that the probability of rolling a 1 on a die is 1 over 6? What does that statement actually mean, right? Because I'm sure you're all willing to make that statement, but what are we saying when we say that? And so I'll give you a second to pause if you want. But what I'm hoping to get at with this question is that the meaning of a probability is not entirely clear, or at least you have to think a little bit about it. Right? Because, of course, once I roll a die, the outcome is going to be determined. And you can't have sort of fractional outcomes on a die, right? There's never going to be a case where you've rolled the die one time and 1/6 of it came up as the number 1, right? And so we have to be talking about something else. And I think that with rolling a die, it's sort of easier to think about the fact that, well, you could repeat that a bunch of times. And so the 1 out of 6 is somehow going to be capturing what we expect the behavior of this to be in the long term. But of course, this is sort of hard to reason with, right? Because oftentimes we're going to be looking at events that, while we still want to talk about probabilities for, we can't really think about the long term as clearly, right? So what does it mean if a treatment has sort of a 50% chance of curing some disease, right? Well, any person's probably only going to get that treatment once, right? And if it cures the disease and they're healthy, then that's great. But if not, well, what does the 50% probability mean there? And so we have to sort of use our intuition about, say, rolling dice, something that we can repeat very often, to learn how to reason about probability a little bit better. And so there are several ways of interpreting probability, but sort of no matter which way we're looking at, probability is going to be assigning a numeric value to different events, and we're going to be trying to describe their likelihood in some way, right? So sort of no matter your interpretation, that's what a probability is. It's a number that talks about the likelihood. In this course, and sort of the dominant view throughout most courses that you could take, is going to be what is known as the frequentist interpretation of probability. And in my opinion, the frequentist interpretation of probability is actually the easiest one to think about. So from this vantage point, within the frequentist framework, the probability is the long-run proportion of times that an event occurs. Right? So when we say that the probability of rolling a 1 is 1 over 6, what we mean is that if we were to roll this die millions of times, say, that in roughly 1/6 of those events, we would see a number 1, right? And so with frequentism, what we're thinking about is sort of frequencies define probabilities. And we're also sort of thinking about, at least hypothetically, running an experiment over and over and over again, right? So if you repeat the experiment many, 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 many times, then you could count the frequency of times that this occurs. And that's how we're going to be defining probabilities. So whenever we're talking about, say, the probability that a medicine works, then what you're thinking about is if you were to give that medicine in this situation many, 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 many times, it would work in some proportion of cases. Okay. There are other ways of describing what the probability is. We're not going to focus on those in this course, but if you're interested, you can certainly read up on them. Now, with sort of a knowledge of what probability is, we can start to think about it as a mathematical construct a little bit better. And so there are three basic properties or axioms that define valid probabilities. So we can think about probabilities as sort of being a map, right? We talked about it's a numeric value that's assigned to any possible event, right? And so we need to map our events to these numeric values. And so what defines a valid map? Well, the first is that every event has to have a probability which is non-negative, right? And if we're thinking about them as sort of a frequency, this makes sense, right? You can't have a negative frequency of things. If you were to run an experiment 1 billion times, you can't have a negative number of occurrences of any particular event. You could have 0, but you can't have a negative number. So probabilities have to be at least 0. Now, if we look at our full sample space, which I'll remind you is denoted with this script S here, the probability of the full sample space has to be 1, right? And so if we think about what that means, well, an event occurs anytime that any elements of it occur, right? And our sample space is anything that could possibly occur. And so in 100% of cases, we observe something from our sample space. And again, this sort of follows from the definition of what a sample space is. It's all possibilities that could come from our experiments. And so because of that, the chances that we observe something in, say, our billion experiments that are in our sample space are 100%, right? It's every single time we're going to observe something from our sample space by definition. So the probability of a sample space has to be equal to 1. And now the third axiom, sort of the most confusing to write down. But if we have a collection of disjoint sets, right? And so we'll just label those A1, A2, A3, and so on. And we're going to assume you could have possibly infinite number of them, but sort of, one corresponding to each of the integers. Then if these are disjoint, the probability of observing the union of all of them, right? And so if we remember what's the union is any of the events in any of the different sets. And because they're disjoint, there's no overlap, right? So it's all of these sets sort of individually. The probability of observing the union is going to be the sum of all of the probabilities, okay? And again, this is sort of an intuitive idea. If you think about the events as being a 1, we're rolling a die, and you want one of your events is roll a 1, one of your events is roll a 2, one of your events is roll a 3. Well, the probability that you roll a 1, a 2, or a 3 is going to be the probability that you roll a 1 plus the probability that you roll a 2 plus the probability that you roll a 3. Right? And so probabilities have to sort of preserve that additivity. Now, I'll point out that disjoint here is a very important term, right? Because let's say that the probabilities that I'm interested in are, say, the probability that I roll a number which is less than or equal to 3, right? Or the probability that I roll a 2, okay? So if you're thinking about this, the event that you roll a less than or equal to 3 is going to be 1/2, right? There's in 1/2 of cases, you could roll something that's less than or equal to 3. And in 1/6 of cases, you could roll something that is a 2. And so if you were to say that those add, then you'd say that 4 out of 6 times you roll something that is less than or equal to 3 or is equal to 2. But of course, that's not the case because the 2 is contained within that less than or equal to 3, right? And so the probability that you roll something which is a 2 or is less than or equal to 3 is going to be 1/2, right? It's no different than just being less than or equal to 3. And so in order for this axiom to hold, we require that the sets are going to be disjoint. Those are the three properties that define what a valid probability is. So if you have some sort of mapping from your sample space to the real line that follows these three properties here, we say that it's going to be a valid probability. It might not be the one that corresponds to the real world, but it will at least be mathematically valid. we need to make these assumptions about probability in order to work from here. But once we've made these assumptions, we can start to generate a lot more useful properties, right? And so we can think about what I'll call the derived properties of probability. And I'll go through several of these here, and we'll start to see them as we work on examples. And I'd encourage you to sit down and see if you can sort of at least reason about why these are the case, even if you can't sort of formally prove it. So we talked about what complements are, right? And so the complement is the probability of the complement of an event is going to be 1 minus the probability of that event, right? So the probability that you roll a 1 is 1 over 6, right? So the probability that you don't roll a 1 is going to be 5 over 6, right? Again, it's intuitive. You can get there from the axioms that we defined. The probability of the empty set is taken to be 0. And this sort of follows from that first derived property, as well as the probability of the sample space being 1, right? Because the empty set is the complement of the sample space. And so because of that, we can sort of derive this property here. Now, with any event, we need that the probability is at most 1. And again, this should sort of make sense. We can't have probabilities that are bigger than 1. But it turns out that we don't need to make this as an assumption. This follows from those axioms of probability. Now, if we have two different events, the probability of the union of these two events is going to be probability of the first event plus the probability of the second event minus the probability that both events occur, right? Minus their intersection. And I'd encourage you to write this down with a little Venn diagram and sort of convince yourself of this. But this is exactly the case that we were just talking about, where with rolling a less than or equal to 3 and rolling a 2, right? And so you could fill in the probabilities there. Less than or equal to 3 is 3 over 6. Probability of rolling a 2 is 1 over 6. So add a plus b, we have 4 over 6. But the intersection is also going to be 1 over 6, right? Because the intersection is rolling a 2. And so then we're back to 1/2. Right? And so this is the general rule. The axiom is only for disjoint probabilities. Now, you can start to expand this, right? So if you have 3 events instead, you're going to sum up all of them, and then you're going to take away the 2-way intersections, and then you're going to add back the 3-way intersections, right? And then if you had more, you could add all of the 3 ways, start taking off the 4 ways as well. Right. And so this is going to be sort of the general way that you could expand this out. It's not common that we're going to be looking at sort of more than 2 or 3-way intersections. The other thing that I'll point out from this is that these probabilities allow you to define the probabilities of intersections, although we'll look at those in more detail later on. Now, with those sort of properties, there's this question of how do we actually come up with what the probabilities are, right? So we talked about what a probability is, and we said that that was going to be the long run proportion of times that something occurred. But we can't actually sort of derive probabilities that way most of the time. And so one of the useful notions in terms of calculating probabilities is the idea that all outcomes from an experiment are equally likely. Now, this isn't always going to be the case, but in a lot of experiments, it is going to be the case, right? And so if we assume that all of the outcomes from an experiment are equally likely, and that there are capital N total events, right? Then we can use these two assumptions to actually assign probabilities to events. And so the way that we'll do this is by supposing that the event A, which is the event that we care about, has N sub A different ways of occurring, right? If we make those assumptions, then the probability that A occurs is N sub A over N. So think about that probability of rolling less than or equal to 3, right? There are 3 ways of that occurring. You can roll a 1, you can roll a 2, or you can roll a 3. So N sub A is going to be 3. Of course, there are 6 possible numbers that can come up on a die. So the N is going to be 6. And so we have 3 over 6 or 1/2. And that's how we could get there, sort of using these formal notions here. But of course, this is going to be a lot more helpful for us when we start to work with more complex probabilities than just rolling a die. So that was a lot to cover, probably, and so I'd advise you to go back over and look through those axioms, make sure you understand the 3 properties there, as well as all of the derived properties that we looked at, because they're going to be useful for us when we're doing probability calculations. To summarize sort of the key points, though, In this course, we're thinking about probabilities in the way that a frequentist would, which is to say the long run proportion of time that event occurs. We have our three basic axioms of probability. So we have positivity, we have the unitary property, or the probability that the whole sample space equals 1, and we have additivity. We can get further properties by manipulating those axioms. And the value of a probability can be assigned if we suppose that you can count up the different ways that an event can occur, assuming that all possible events have the same likelihood of occurring. Right? And so this was sort of our first foray into actually looking at the mathematical study of probability, and we're going to continue this in the next lesson, and so I will see you all there.